Okay, today's topic is our first lecture on the last module of our topic, that is generalized theory of electrical machine. Now, in generalized theory of electrical machines, what we will discuss is that first we need to understand the essence of studying this particular topic. That one thing, if you observe as of now, what we have studied that was applicable to the model which we developed is based on different assumptions, simplifying assumptions, and it was mostly for addressing the steady state analysis. But means all this model, if you study that when that synchronous model equivalent circuit was developed, or the genesis of Blondel two reaction theory, at this moment I cannot recall the exact year, but it is quite early 90s, and 1900 century means it was there. Means now when we are means at the first part of 20th century, it was all was over. Now, so now the thing is that if you consider the age of 1980 onwards, even before 1980 there was some means gross improvement in your tangible change in your computational device in terms of means people started, and in 1980-85 we got our microprocessor, and after that in after 1990 we started means having our own computers, means our now while this computer is there, that computer makes or gives birth of a particular stream, or means an idea, that is analyzing electrical machine in computer. Now this is quite different than what I normally discuss in my usual class, that is optimization program to find out an optimal design for a given machine. This is chiefly about analysis. Now, while we are thinking about analysis, we need a program. So, if we means supply that program the machine parameters, it will let us know, or it can simulate the machine performance, right? It can simulate our machine performance, but there is one slight problem is there, that with our means time, now we are having, with times we are having machine with different structures, like nowadays your Tesla 3 is having a motor which was not known to us 10 years back. We couldn't imagine that kind of motor structure. So the question here we need to answer is that what should be our approach, means how should we proceed, like what we will do, whether we will go for individual machine program, or can we have a generalized machine model in which all the machine, means all the rotating machines and also transformer can be represented just by suitably considering that machine. So if you have that generalized kind of representation, what is now why this the idea of generalized structure is not an utopic one is that if you consider uh, my lecture in your last semester on electromechanical energy conversion, you will find that there is a few similarities exist between different electrical machine. Either the machines are singly fed or double fed. What is the example of single fed machine? Like your induction machine, normally your reluctance machine. What is the example of double fed or doubly fed machine? Synchronous machine. Now here in case of synchronous machine, you may get confused considering standalone synchronous generator, but if you just become a bit more flexible and think of a generator that is connected to grid, your confusion that will help you to remove your confusion. And then you are having your DC machine. All these are in motoring mode, they are doubly fed. Now, generally what machine we will get, either they are single fed or double fed. Another thing is that in all the machine, only two way the EMF will means we can observe or we can watch that the EMF is getting induced across the sheet of EMF winding. We can say winding is a sheet of EMF. The EMF induced across winding, whether rotor winding or transformer secondary winding or any other winding, armature winding, everywhere EMF can be induced using two different technique, like based on their nature of this induced EMF. One is also known as transformer EMF, which we get in case of transformer, in case of induction motor, and another one is dynamically induced EMF, or also known as motional EMF. So what is the difference? Here the field is time varying and the other side of the conductor, the sheet of induced EMF, experiences flux variation due to the time varying nature of that field, and EMF is getting induced there. And what about dynamically induced EMF? The field is somewhat more or less constant, but the field is varying in space, and therefore they represent dynamically induced EMF. Now, while we are finding out this commonness between, or means commonness among all our machines, long back celebrated professor of electrical engineering, is pioneer in this field, Professor Gabriel Cron, he made uh, means interesting, and that is a kind of means that gives birth of this whole new uh, type of analysis. What he observed, let me write in his word. Let me use another color. The division of the division of a voltage vector into induced and generated. By induced he is meaning statically induced EMF, and generated means dynamically induced EMF. Generated voltages is uh, this is the most beautiful observation he has made. See, I have highlighted the word relative. Why this relative is important, that I will discuss, but let me complete his statement. On the reference frame, this is very important term, reference frame. In explanation of this sentence, he elaborated further. A certain voltage vector may be entirely induced or entirely generated voltage, or uh, just a minute, let me check whether it's recording or not. Generated depending the on the relative velocities of the reference frame and conductors means the seat of EMF. Another very important statement, only he can make such a powerful statement. So this is a statement that has changed the entire uh, analysis procedure of electrical machine, and that is why we all are grateful, and means whatever we express our means we cannot thank him enough for his contribution. Why I am so means trying to highlight his contribution to such a means to emphasize his contribution, because gradually as we will proceed you will be able to understand how powerful these statements are. These 3 or 4 sentences, how powerful they are. First, try to understand the division between here, the division of a voltage vector into induced and generated. Induced means statically induced. You can write transformer EMF, and this is motional. Motional is what you get in your DC machine. What he says is a relative concept. Try to understand the beauty of this word relative, and depends entirely on the reference frame. Now, suppose consider a transformer. You apply primary. Now, what type of flux is being generated by your primary? If you try to visualize the motion of flux through the core, you will see that flux is executing a to and fro motion through your magnetic core, means magnetic material core. Now, that flux is space invariant, and that flux links with your secondary, and thereby some EMF is getting induced across your secondary winding. Now, suppose if you have a bar magnet, what I am trying to say, that where can I draw? Yeah, let us consider that we have a transformer like this. Now here you are having your flux lines. In one time it is moving in this direction, in the next instance it is moving in opposite direction, because current through this, sometimes it is flowing in this direction, sometimes it is flowing in this direction. It is clear that this flux is executing an alternating motion, and therefore the secondary side is experiencing a time varying flux. So if you consider the secondary side is in a standstill reference frame, it is getting this flux. Now consider that here as if you have uh, instead of this like this one, suppose you have uh, how to explain. Okay, now instead of providing a DC, sorry, as AC, let us do what? Let us apply a DC voltage here. Again, don't get confused and make noise that if we put DC on a transformer, it will burn out this, that. Say it is a small DC, it's a very nominal value, but strong enough to generate a magnetic field. Now, suppose this winding is loosely wound on this structure. And what you can do is that you can totally means take this whole thing together with its DC excitation, like here, means what I am trying to say that after certain instance your coil reach here, means this was your original coil, so you are allowing this coil, means you are feeding this primary side coil with DC, but what you are doing, you are moving this primary side coil in this way and in this way. So how this will affect this secondary? When the coil is here, it will experience a flux, but when it will reach here, it will experience a flux variation. So even you are giving the DC to your transformer primary, but if you allow the transformer primary to move or means slide on your core, means slide through that means core periphery, then still it can give you, your secondary will realize a time varying flux, and but that flux is how, what type of flux? That is a motional flux. Even if you find it difficult to understand, then what you can do is that consider a hollow pipe, a square shaped pipe, right? uh, Say this. So this is a hollow pipe. Now you place or you own an winding here, and then you are placing a bar magnet, and somehow you are allowing this bar magnet to continuously rotate through this hollow pipe. This bar magnet is inside this pipe, it is rotating. So don't you expect this, can't we expect that here we will, if we connect a voltmeter, then this voltmeter will give us a deflection. If this means one continuously rotate in this manner, north south, north south, north south, Oh, that means it is what, and that same kind of thing you will get if you replace this magnet by another coil here and feeding some alternating voltage sources here. You will get an alternating voltage induced across this. Now, now when you are considering this second case, this is a transformer EMF, but you can get the same magnitude of EMF by allowing uh, or by moving a bar magnet through this hollow pipe. Obviously, this represents an air core transformer, but I'm not talking about that magnetizing current, power factor, all these things. I'm talking about that what Professor Korn uh, uh, wanted to or point out, or what was his intention behind this statement, that same EMF can be considered as rotating or dynamic EMF. Now, static or dynamic EMF. It all depends on how you are trying to see it. And also, you can have, if you have this kind of setup, you can reduce the strength of this alternating voltage, and you allow flow of means allow, not flow, rather than motion of a bar magnet through this hollow chamber. So the total voltage still remains same. That means now it becomes this part, that first one, voltage vector may be entirely induced. When there is no bar magnet, it is entirely induced. When there is no winding, only bar magnet is executing a motion through this hollow chamber, then it is totally generated. And when both of them are present, then, but it is only the relative velocity of the reference frame and the conductors. Now, it may sound weird to you, because what is relative velocities of the reference frame of the conductor? Reference frame of the conductor, this reference frame can be attached with that conductor, or it may be attached with the flux lines, or attached with something else. Like here, if we consider this example, when the reference frame is attached with your secondary, then it is an induced EMF. And when the reference frame is attached with that flux, then it means, think about it, it is a flux that executes motion, means in one time this flux execute a motion like this, a clockwise motion. In the next instance, the flux execute a motion like counterclockwise motion, right? So if somebody now sit on the flux, what he will observe, that after some time he will reach, means periodically he will be passing by this secondary side coil. So this periodic means as if you are in a that like so now this bar magnet will be like an observer sitting on a seat of a carousel. Now this observer for this observer, it will be the secondary winding will be a seat for generated EMF or motional EMF. It is not the seat for induced EMF. But when you are just change your reference frame and attached it with your secondary winding, you will see it will be like you are having uh, induced EMF. And when you have both of them, like you place it in such a way that neither it is attached to your secondary nor it is completely rotating with your flux line, you select some different one, then you may get a different notion. Now, but the last sentence is most beautiful. Although most is not a correct adjective that goes with the word beautiful, but we can say always most powerful statement because in your last semester, one student brought it to my notice. Celebrated professor of physics of MIT, Professor Kevin Lewis, and means he is making comment on Kirchhoff's law, and some YouTubers, Electro Boom or somewhere, they are trying to means like although that was somewhat I found both of them are more or less prejudice, means their prejudice are the things that play the key role, not their logic or any analysis. However, so what that Kevin Lewis and Professor Kevin Lewis and Electro Boom, they were having a Electro Boom is a YouTube channel. They were having a heated conversation. Means both of them probably uploaded a few videos. One student, Ayushman, he brought it into my notice. So, and also there is explanatory video from Professor H.C. Bharma. Although it was, if you compare the video from Electro Boom and also video of Professor Kevin Lewis, I found Professor H.C. Bharma's video was most sane and logical. Means in science and engineering, we should not place our prejudice above our logic or analysis. We can be wrong or we can have just a different perception. It is not like that we are having a mixed martial art fight that either you win the belt or your competitor win the belt. Anyway, so see, Professor Crown at that means early age, he might have suspected that people may start this kind of duel and start fight with their prejudice. So he made the last statement, last sentence here. It's the most powerful one. That however the sum of the induced and generated voltage is constant no matter what the reference frame be. Means whether you consider this is Kirchhoff law, that is Kirchhoff law, it is valid, invalid, it is Faraday, it is Kirchhoff, whatever you do, the sum of induced and generated voltage is constant, and that is what you are going to apply when you are going to work. It is not that you have a prejudice that no, this is induced EMF. We can't accept this to be tagged as generated EMF. Another person comes and suddenly jumps in the figure, means in the picture, claiming that no, this is generated EMF. This can't be tagged as an induced EMF. So to means Professor Cron, probably he was a person. Obviously, he was a must be a visionary person also. So he figured out that people may start duel with that too. So he made it very clear that whatever you do, that sum will remain constant, whether you consider it a contribution of Kirchhoff or contribution of Faraday, contribution of Maxwell, contribution of these, that, whoever it is. Physics or physical system doesn't care about who was means who observed which principle, which physical phenomena. It always obeys its own law of physics, and it works in that way. However, problem with Professor Rond is that he was means he was means if you ask me, and this is also means this statement is also coming from many means like established figure and stalwarts of electrical engineering. They consider Professor Ron more or less a mathematician and physicist than that of an electrical engineer. Professor Tron has a classic means has written a classic book. If you ever get a chance, you can read it. The name of that book, if I do not make a mistake, the name of that book is Tensor Analysis of Electrical Circuit. So this probably this was the name of that book. Very means a book that can enrich a mathematician also, but written by a professor of electrical engineering. Anyway, but what was the problem associated with this complicated concept of tensor? Tensor is a more generalized way to represent a vector. How tensor and vector are different, I am not going to that. Professor Kron had developed everything in terms of tensor. Now, these kind of intricate mathematical concepts were creating difficulties in average electrical engineering, means whether they are for practicing engineers, it was means totally means too sophisticated and too complicated for them to crack it, and even for the engineers who are in research, they found it a bit difficult to understand. So at that time, other professors of electrical engineering like Professor N. Hancock and Professor Chi Mung Ong. Chi Mung Ong came to a very later stage of this development, but Professor Hancock, Professor Gibbs, many people came and rescue of these people who were actually kind of deprived of enjoying Cross's brilliant work and his excellent philosophy, just because Cross's presentation was more like a mathematician than that of an electrical engineer. So what they did a very simple thing. They just replace, they discussed and figure out that in most of the cases it is vector that is sufficient to analyze a system. But even if you do not know tensor, if all it is like you open Cron's, suppose somebody gives you Cron's document in .docx or in any editable format, you just select Ctrl F to find the word tensor and just hit Ctrl R to replace it by all that tensors are replaced, more or less replaced by vectors, and some part are dropped because those parts are too means complicated to be understood by normal electrical engineering people. So with that, as soon as they replaced it, it become the Professor Cron's creation becomes available to everyone, because electrical engineers being electrical engineering students, mostly we have and working knowledge in vector, as well as at that time there was CL Foster Q and other people who are dealing and developing theories like symmetrical components already we have discussed. So all these concepts they have already developed, they were there dealing with that. So those people were giving concept based on matrix analysis and linear algebra. So once this tensor replaced by vector, people find that having average knowledge and working knowledge in linear algebra is sufficient to fathom this part. And they started utilizing this quants concept. Actually, quants, in addition to this, develop a primitive machine. That primitive machine of first kind was so generalized that you take any machine, as of now, whatever machine has been developed, can suitably be represented by that primitive machine. Anyway, before we go further digging quants work and understand how powerful they are, we need to educate ourselves with a few keywords that we will find may be helpful in the due course of our discussion. So now let me write those names. Now, in addition to that vector, a few things we must educate ourselves with the nomenclature. That one is that depending on their nature, the reference frame can we can have three different types of reference frames. One is quasi holonomic reference frame. Another one is non holonomic reference frame. And the third one is holonomic reference frame. So if we consider all these reference frame, what is quasi-holonomic reference frame? Quasi-holonomic reference frame is that where it is that part in quasi-holonomic the axis or quasi-holonomic or stationary reference frame, the axis remains stationary, means axis of the reference frame attached to the stator and the rotating part rotates. At a not constant, rather a particular speed, right? Now this that stator system coincides with the reference frame, but there exists a relative, try to understand that there exists a relative speed relative speed difference between the rotor and the reference frame. Obviously, because rotor, if the rotor rotates at a particular speed, then there will be a relative speed difference will always exist between the frame that is attached to the stator and stationary. So the name quasi-holonomic or stationary reference frame. Now, what is non-holonomic? In non-holonomic, what we have is that in non-holonomic the reference frame rotate, but it rotates at a speed it is the speed is different from stator as well as from rotor. So neither its speeds match with rotor nor it matches with stator. And finally, in case of holonomic reference frame, what we can observe is that the your axis of the reference frame are stationary, like the means what is the essence of this reference frame? In this holonomic reference frame, there exists no relative speed difference between the reference frame and the stator and the reference frame and the rotor. Means one reference frame is attached to stator, another reference frame is attached to rotor. Once again, in quasi-holonomic, only one reference frame attached to stator, no reference frame with respect to rotor. What do we commonly understand? What we did in our fundamental theory of rotating electrical machine. Now, second one is what? Second one is non-holonomic, where the reference frame rotate, but it is means neither it attached to stator nor it attached to rotor. It rotates at a different speed. Therefore, it's see, if you consider in terms of angle, sometimes it will lead your rotor axis, sometimes it will lead, sometimes it will lag, because the relative speed is different. And what about this axis of your means here this case you can consider as if you are trying to draw two signal of different frequency in a same phasor diagram, what would happen to them? The third one is that holonomic. Some axes are fixed to stationary stator, the other are fixed to the rotor. Now, this one that these like why these reference frames are very important, that we will discuss. Now, another few terminology of our electrical network that we will use. Obviously, in any electrical circuit, what we always have three different types of circuit element, that is resistor, inductor and capacitor. Now this they join together either in series or in parallel. So now the parameter like okay, and another thing is that when you have many circuit elements joined, one end of the circuit elements are joined to a common point, then that is known as node. I know you know all these things, but still, and when there are different circuit elements connected together, this forms a mesh, right? In other words, you can say the part of the network in which the same current flows, called the branch, like which one or several are in series. I hope you still recall a lesson of graph theory, so I'm not going to dwell with all this, but let me tell you something that you must I don't think you have encountered in your graph theory class, that is the concept of contravariant vector and covariant vector. What are they? That contravariant vector is that one set of vector that are independent so then they will form contravariant vector, and there will be a dependent vector that will be give us covariant vector. It is like if you have linear equations, say y is equal to say y is equal to minus 3x1 plus 2x2. Y1 is equal to minus 3x1 plus 2x2, and y2 is equal to say some minus 4x1 plus x2. So here this x1, x2, they are like your independent one, and this y1, y2 are the dependent one. And what about your orthogonal network? We know that orthogonal network is defined as the collection of both meshes and junction part. Okay, in terms of the covariant vector, how we can represent things. In meshes, what is independent? In meshes, the mesh current flowing round the meshes are can be treated as independent variable. So in mesh, you can write that mesh current forms our contravariant vector, while the coil voltage that form the covariant vector for a mesh network. Alternatively, in case of a node analysis, the node voltage plays the role of contravariant vector and node current that is dependent on the node voltage is the covariant vector. And what about our orthogonal network? Orthogonal network is defined as a collection of both the meshes and nodes. The contravariant variables of contravariant variables of these two networks are independent, linearly independent. But knowing one set of contravariant vector cannot help us to figure out the other set of contravariant vector. Linearly independent means that always add one more dimension to your information. Say y is equal to mx. This is one equation in xy plane. Now y is equal to say 2x plus 3. These two equations are independent and they intersect each other at a particular point. So this point is very important for us to understand that this gives us the point where our solution meet, right? So I hope you know all these elementary things. In our next video we will discuss on that how we can introduce transformation to analyze our electrical machine, right?